And now in this lecture we'll find out the shaded area. In the drawing we have a circle that is inside this quarter circle. In addition, we know that the radius of this circle r equals to the square root of 2 units in its length, and our mission is to find out the value of this shaded area. Okay, so first of all we will define this point as point A. We'll define the center of the quarter circle, this point is O. We'll define the touching point, we'll define this point as point B. We'll define this point as point C. We will define this point as point D. We'll define the touching point here between the circle and the quarter circle, or the point of tangency between the circle and the quarter circle as E. And we define the center of this circle as F. In the next step, we join points F and C together by a straight line. Point F is the center of this circle, point C is a point on the circle itself, therefore line segment FC is the radius of this circle, that is actually equals to to the square root of 2 units, according to what is given us the question. Here we can implement rule 1. I'll repeat quickly on rule 1. According to rule 1, the tangent to the circle is perpendicular to the radius drawn to its point of tendency. In the drawing we have this circle and tangent AB, that is tangent to this circle, at this point, point M. Point M is the point of tendency. And we have the radius OM that is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees. You can actually implement this rule 1 in our drawing. Why? Because in our drawing we have the radius FC that is drawn to point C, that is the point of tendency of tangent OD with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent OD will be perpendicular to the radius CF. If OD is perpendicular to CF, then this angle will be equal to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have here the radius FB that is drawn to point B, that is the point of tendency of tangent DA with this circle. And whenever your radius that is drawn to the point of tendency, then tangent DA will be perpendicular to the radius BF. If DA is perpendicular to BF, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we will focus on this small quadrilateral BFOC. Inside this small quadrilateral BFOC, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, plus this the fourth missing angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing angle here must be equal to 90 degrees in its size. Again, in order to complete the sum of the angles inside this quadrilateral BFOC to 360 degrees, the missing angle here must be equal to 90 degrees in its size. So inside quadrilateral BFOC we have 4 right angles. Therefore, quadrilateral BFOC must be at least a rectangle if not a square. So we relate to this small quadrilateral BFOC as a rectangle, and we also know that the opposite sides of a rectangle are equal to each other. That is to say, side BF must be equal to the opposite side OC in rectangle BFOC. But BF equals to the square root of 2 units. BF equals to the square root of 2 units, therefore OC must be also equal to the square root of 2 units. Likewise, according to the sum rule, in rectangle BFOC, side FC must be equal to the opposite side BO, but FC equals to square root of 2 units. It is the radius of the circle. Therefore, BO must be also equal to the square root of 2 units in its length. So actually we found out that quadrilateral BFOC is not a rectangle but a square. Why? Because all of its sides are equal to each other. Each side equals to the square root of 2 units in its length. Okay. In the next step, we join points O and F together by a straight line. And joining points O and F, we created the right triangle OBF. The right triangle OBF is also an isosceles triangle, because those two sides are equal to each other, and we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha because they are equal to each other. And we also note that the sum of the angles in any triangle is equal to 180 degrees, and especially it is true in the right and isosceles triangle OBF. So in this right triangle OBF, the sum of the angles must be equal to 180 degrees. So which angles we have inside the right triangle OBF? We have this angle is a right angle, it equals to 90 degrees. So 90 degrees plus alpha, in total it must be equal to 180 degrees. So repeat again, in the right triangle OBF, the sum of the angles must be equal to 180 degrees. So 90 degrees plus 2 alpha must be equal to 180 degrees. Here we subtract 90 degrees from this equation, and finally we get that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. Here we divide this equation by 2, and finally we get that the missing angle alpha equals to 90 degrees over 2 is 45 degrees. So actually this is angle alpha is equal to 45 degrees in its size, and this is also angle alpha that is equal to 45 degrees in its size. In the next step, we will extend line segment OF by a straight line until it touches the circle and the quarter circle. So here we have rule 9. Repeat quickly on rule 9. According to rule 9. If two circles touch each other internally, then the straight line that connects their centers together must pass for their touching points. So in the drawing we have two circles. The small circle touches the big circle at this point, point P, or point P is the touching point between the two circles, or point P is the point of tendency between those two circles. And according to this rule 9, here we have the center of the big circle is at point O. The center of the small circle is at point M, and the straight line that connects their centers together is the straight line OM. So this straight line OM must pass for their touching point. That is to say, the straight line OM must pass for point P, or OMP is one straight line. Again, according to rule 9, OMP is one straight line. Okay? So whenever you have an internal notch between two circles, that is to say, if two circles are touching each other internally, then the straight line that connects between the centers together must pass for their touching point. In this case, OM, the straight line OM that connects the centers together, passes for point P, or OMP is one straight line. So we can actually implement rule 9 in our drawing. Why? Because in our drawing, the small circle touches the big quarter circle at point E. So we have an internal notch between those two circle and the quarter circle, that is to say they are touching each other internally at point E. Point E is their touching point, or their point of tendency. So here, the straight line, the center of the quarter circle is point O, and the center of the circle is at point E, at point F. The straight line that connects their centers together is the straight line OF. So according to rule 9, the straight line OF must pass for their touching point, that is to say point E. Or OFE is one straight line. OFE is one straight line according to rule 9. Here we define the intersection point between line segment OF and this circle is point H. So if OFE is a straight line, it means that edge FE is also a straight line. Here, edge FE is also a straight line. But the straight line edge FE passes for point F, that is the center of the circle. And so therefore, first of all, edge FE is a straight line that touches the circle at 2 points, point H and point E. Therefore, edge FE is a chord. Edge FE is a chord inside this small circle, and the chord edge FE passes for point F, that is the center of this circle, and any chord that passes through the center of the circle must be the diameter of the circle. Therefore, edge E is the diameter of the circle. Write it here that edge E is the diameter of the circle. 9/7 edge E. This 9/7 edge E is the diameter of the circle. And we also know that any diameter of the circle divides the circle into two halves. Each half is the semicircle of the circle. So this is the first semicircle, and the second half is the other semicircle. So this is a semicircle. Okay, so this is a semicircle, edge E, B is a semicircle, and again our mission is to find out this shaded area. But here we know that point F is the center of the circle, point E is the point on the circle itself, therefore FE is the radius of this circle that is equal to square root of 2 units in its length according to what is given us the question. Here we can implement the Pythagoras theorem on the right triangle, the right and the associated triangle, triangle OCF. In the right and the associated triangle, triangle OCF, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, OF square equals to OC square plus CF square. According to the Pythagoras theorem, put again in the right and the associated triangle, triangle OCF, OF square equals to OC square plus CF square. So OF square, that is the square of the hypotenuse, is equals to OC square. OC is square root of 2, therefore OC square is square root of 2 squared, that is 2, plus CF square. CF is square root of 2, therefore CF square is square root of 2 squared, that is 2. So in conclusion, we found out that OF square, that is the square of the hypotenuse, equals to 2 plus 2, that is 4. Here we take root out of this equation, and we get that OF equals to the square root of 4, that is 2. So the hypotenuse, the length of the hypotenuse OF is equals to 2 units. Here, the hypotenuse OF of the right and associated triangle OFC equals to 2 units in its length. And we have already found out that OFE, actually we only found out that OFE is one straight line. Here OFE is one straight line. Want it here that OFE is one straight line. If OFE is one straight line, what is the definition of the straight line OFE? Point O is the center of the quarter circle, point E is the point on the quarter circle itself. Therefore OE is the radius of this the quarter circle. We'll define the radius of the quarter circle as capital R, and the radius of this small circle will be defined as R. So the radius capital R of the quarter circle will be equal to OF plus FE, because OFE is one straight line. Therefore OE is one straight line. So the radius R equals to OF plus FE. Write it down here. The radius R of the quarter circle equals to OF plus FE. So the radius capital R equals to OF, that is 2, plus FE, that is square root of 2. So we actually found out capital R equals to 2 plus square root of 2. So we found out that the radius of the quarter circle R equals to 2 plus square root of 2. Plus square root of 2, while the radius R of this circle, the small circle, equals to the square root of 2. Okay? So, what is the value of this shaded area? what is the size or the value of this shaded area? The shaded area will be equal to the area of sector AOE repeat again, the value of this shaded area will be equal to the area of sector AOE, this sector, minus the area of this semicircle, minus the area of this shape that we can define it as shape BHO. This one, shape BHO. Repeat again. Our mission is to find out the size or the value of this shaded area. From the drawing itself, it is very easy to see that the value of this shaded area equals to the area of sector AOE minus the area of this semicircle minus the area of this shape BHO. Repeat again. The shaded area in total it is equals to the shaded area in total it is equals to the area of sector AOE minus the area of the upper semicircle minus the area of shape BHO. So we find out the area of which shape, and then we subtract them from the area of sector AOE, and this will be the value of this shaded area and the answer to this question. So first of all, we find out the area of sector AOE. Actually, what is the area of a sector? So if we have a circle and the radius this is the center of the circle. The radius of this circle is R, so here those are the two radii of the circle. Sector AOB, or shape AOB is defined as a sector. Shape AOB is defined as a sector. We define the angle between the two radii as theta. Sector, it is like a slice of cake. If we define the circle as a cake, then a slice of a cake is the definition of a sector. If this is a cake, then this is a slice of a cake that is actually a sector AOB. So what is the area of this sector? The area of sector A or B. This is how we here the sign here, the roof over A or B is the sign for a sector. So this is how we define the area of a sector. So the area of sector A or B will be equal to pi r squared, that is the area of this circle, times the angle between the two radii, that is theta, over 360 degrees. This is the formula for the area of any sector. Okay, so we'll implement this formula in our drawing in order to find out the area of this sector A or B. So the area of sector A or B here, this is the area of sector A or B. This is the sign for the area of sector A or B. It will be equal to the area of the big circle, that is pi times capital R squared, times the angle between the legs of the sector. We have one leg that is OE and the other leg of sector AOE is OA. Those are the two radii of the big circle, that is to say they are equal to capital R. OE equals to capital R and OA also equals to capital R because it is the radius of the big circle. So pi r squared is the area of the big circle times the angle between the legs of this sector AOE. The angle between the legs of sector AOE, the size of this angle is 45 degrees. Why? Because BOF is a right triangle is also and also isosceles triangle. So angle BOF equals to 45 degrees. So the angle between the legs of sector A or B is equals to 45 degrees over 360 degrees. So it is pi, and we have already found out that capital R equals to 2 plus square root of 2. Capital R equals to 2 plus square root of 2. If capital R equals to 2 plus square root of 2, it means that capital R square equals to 2 plus square root of 2 square. 45 degrees over 360 degrees is equals to 1 over 8. So we divide it by 8. This is the area of sector A or B. So here we have pi times 2 plus square root of 2. This is actually equals to 2 squared, that is 4, plus square root of 2 squared, that is 2, plus 2 times 2 times square root of 2, divided by 8. So here we have pi, inside the brackets we have 4 plus 2 is 6, plus 2 times 2 is 4, times square root of 2, divided by 8. Here we divide this expression by 2. We divide both the numerator and the denominator of this expression by 2. And we get that the area of sector A or B in total it will be equals to, we have pi, and here 6 over 2 is 3, plus 4 over 2 is 2. So in total this expression will be 2 times square root of 2. And we divided the numerator by 2. Here we divide also the denominator by 2. 8 over 2 is 4. So in conclusion, found out that the area of sector A or B is equals to pi times 3 plus 2 times square root of 2 over 4 square units. In the next step, we have to find out also the area of the semicircle. We already found out the area of sector A or E. Now we have to subtract from the area of the sector A or E the area of the semicircle. So what is the area of the semicircle? The area of any semicircle is equals to the area of the circle that is pi r squared, small r. And if we divide the area of the circle by 2, we get the area of the semicircle. So the area of the semicircle equals to pi r squared over 2. The area of this semicircle is equals to pi r squared over 2. And it is given us the equation that r equals to the square root of 2. So the area of the semicircle will be equal to pi times r is square root of 2, and if r is square root of 2, it means that r squared equals to the square root of 2 squared divided by 2. So it is pi, and square root of 2 squared is 2 divided by 2. 2 over 2 is 1. So we left only with pi. In conclusion, we found out that the area of the semicircle equals to pi square units. The area of the semicircle equals to pi square units. The area of this semicircle equals to pi square units. And finally, we also have to find out the area of the small shape BHO. The area of the small shape BHO. Repeat again. We have to find out the area of this small shape BHO. Okay, yeah. This is the shape in the orange color is the shape BHO. What is the area of shape BHO? From the drawing, it is very easy to see that the area of shape BHO, the shape in the orange color, is equals to the area of the right and the isosceles triangle BFO minus the area of the small sector FBH. Yeah, on this small sector FBH. Repeat again. The area of the small shape BHO in the orange color is equals to the area of the right in the isosceles triangle BFO minus the area of the small sector FBH that is part of the small circle. It is a portion of the small circle. So the area of shape VHO equals to the area of the right in isosceles triangle BFO. What is the area of the right in the isosceles triangle BFO? It is actually the base times the height over 2. The base and the height, they are both equals to the square root of 2. Yeah. If the base is square root of 2, then the height to the base is also square root of 2, because those two sides are equal to each other. So it is the base is square root of 2 times the height to the base is also square root of 2, and we have to divide it by 2. That is the area of any triangle. The base times the height to the base over 2 is the area of any triangle. So square root of 2 times square root of 2 is 2, and 2 over 2 is 1. So this expression in total equals to 1. That is to say, the area of the right in the isosceles triangle BFO is equals to 1 square unit. And we have to subtract from the area of the right in the isosceles triangle BFO the area of sector FBH. The area of this sector FBH. The area of any sector equals to pi r squared, that is the area of the circle, times the angle between the legs of this sector. The angle between the legs here is 45 degrees. So it is 45 degrees over 360 degrees. 45 degrees over 360 degrees is 1 over 8. So in total, the area of sector FBH equals to pi r squared over 8. R is square root of 2. So it is pi times square root of 2 squared over 8. So it is equals to pi, and square root of 2 squared is 2 over 8. Here we divide this equation, this expression by 2, both the numerator and the denominator by 2, and here it will be equal to pi, 2 over 2 is 1, and 8 over 2 is 4. So the area of sector FBH in total it is equals to pi over 4, and the area of triangle BFO is 1 square unit. So in total, the area of the orange shape BHO, in total it is equal to 1 minus pi over 4 square units. Okay, now we have all the data that we need in order to find out the area, the value of the green, the value of this shaded, the size of this shaded area. Again, the size of the shaded area equals to the area of sector AOB. We have already found out that the area of sector AOB is equals to pi times 3 plus 2 times root of 2 over 4. So this is the area of sector AOB minus the area of the semicircle that is equal to pi, so it is minus pi minus the area of shape BHO that is equals to 1 minus pi over 4 square units. So it is equals to pi times 3 plus 2 times square root of 2 over 4 minus pi. Here we will open the brackets and get here minus 1, minus and minus is plus, so it is plus pi over 4. Okay, so here we have, so in total the size of the shaded area will be equal to pi, inside the brackets we have 3 plus 2 times square root of 2 over 4, and here we have minus pi plus pi over 4 is minus 3/4 pi. Minus 1. So in conclusion, found out that the size of the shaded area is equals to this expression. Here we take from those two expressions 4 as a common factor, or we divide minus 1, we multiply minus 1 by 4 and then we divide it by 4 in order to have a common factor with this expression. And we get that in total the area of the green shape will be equal to pi. Inside the brackets we have 3 plus 2 times square root of 2 divided by 4. So, and minus 3 pi. Here we multiply minus 1 by 4 and we divide it by 4, so it will be in the numerator we have minus 4 divided by 4. So the size of the shaded area is equals to pi. Inside the brackets we have 3. So we'll open the brackets here. Pi times 3 is 3 pi plus 2 times square root of 2 times pi minus 3 pi minus 4 divided by 4. So here 3 pi minus 3 pi is 0, so 3 pi will get cancelled. And after we cancel 3 pi, we left only with 2 times square root of 2 times pi minus 4 over 4. Here we divide both the numerator and the denominator of this expression by 2. And we get that here 2 will get cancelled and we left only with square root of 2 pi and minus 4 over 2 is minus 2. We divide the denominator of 4 by 2, so 4 over 2 is 2. So in conclusion, we found out that the size of the shaded area is equals to square root of 2 times pi minus 2 over 2 square units. Or in terms of numbers, it is equal to 1.2214 square units. And that is the answer to the question. Repeat again. The size of this shaded area is equal to either square root of 2 times pi minus 2 over 2 square units, or in terms of numbers, it is equal to 1.2214 square units. So in the next step, I will summarize the lecture. lecture, we found out the value of the size of this green area or the shaded area. So in the drawing we have a circle that is inside this quarter circle. The only thing that we know here that the radius of this circle is equals to the square root of 2 units in its length. Again, our mission is to find out the size of this green area or the shaded area. Okay, so here we gave names to those points, the relevant points to this question. A, B, O, the center of the quarter circle is O, the center of the small circle is F, the point of tendency or the touching point between the circle and the quarter circle is here at point E, and here this is point C, point D. So here we have tangent OD that is tangent to this circle at point C. Point C is the point of tendency. Here point F is the center of this small circle. Point C is the point of the circle itself. Therefore FC is the radius of this circle that is equals to the square root of 2 units in its length according to what is given us in the question. Here R equals to the square root of 2 units. The radius FC is drawn to point C, that is the point of tendency of tangent OD with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OD will be perpendicular to the radius FC. If OD is perpendicular to FC, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Likewise, here FB is the radius of this circle is equals to the square root of 2 units in its length according to what is given in the question. The radius FB is drawn to point B, that is the point of tendency of tangent AO with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius BF. If AO is perpendicular to BF, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. So inside the small quadrilateral BFOC, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees. Plus the size of the fourth angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing angle must be equal to 90 degrees in its side. Again, in order to complete the sum of the angles inside quadrilateral BFOC to 360 degrees, the missing angle here must be equal to 90 degrees in its side. So actually, inside quadrilateral BFOC we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to this quadrilateral BFOC as a rectangle, and we also know that the opposite sides of a rectangle are equal to each other. So in rectangle BFOC, side BF must be equal to the opposite side OC. But BF equals to the square root of 2 units, it is the radius of the circle. Therefore OC must be also equal to the square root of 2 units in itself. Likewise, according to the same rule, side FC must be equal to the opposite side BO. But FC is square root of 2, therefore BO must be also equal to the square root of 2 units in its length. So actually found out that quadrilateral BFOC is not a rectangle but a square, why? Because all of its sides are equal to each other. Each side equals to the square root of 2 units. Okay, in the next step actually we join points O and F together by a straight line. By joining points O and F, we actually created the right and the isosceles triangle OBF. And we have the rule that here we have those two sides are equal to each other. And we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha because they are equal to each other. And we also know that the sum of the angles in any triangle is equal to 180 degrees. And especially it is true in the right and associated triangle OFB. So which angles we have inside the right triangle OFB? We have this angle that is the right angle, plus this angle that is alpha, plus this angle that is alpha. So here, in the right hand isosceles triangle OBF, 90 degrees plus 2 alpha must be equal to 180 degrees. Here we subtract the 90 degrees from this equation, and finally found out that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. Here we divided this equation by 2, and finally found out that alpha equals to 90 degrees over 2, that is 45 degrees. So this is angle alpha that is equals to 45 degrees in its size, and this is also angle alpha that is also equals to 45 degrees in its size. Okay, so in the next step, we extended the line segment OF by straight line until it touches this circle and quarter circle, and we have here all 9. According to all 9, whenever we have an internal notch between two circles, or two circle and a quarter circle, then the straight line that connects the two centers together must pass through their touching point. So here we have the center of the quarter circle is here at point O, the center of this circle is at point F. So according to rule 9, the straight line OF that connects the centers together must pass through point E, that is their touching point, or OFE is one straight line. Here OFE is one straight line, and here also we implemented the Pythagoras theorem in the right and associated triangle OFC. According to the Pythagoras theorem, OF square equals to CF square plus OC square. Repeat again. In the right and associated triangle OFC, OF square equals to OC square plus CF square. So OF square, that is the square of the hypotenuse, equals to OC square. OC equals to the square root of 2, therefore OC square is square root of 2 squared, that is 2, plus CF square. CF is also square root of 2, therefore CF square is square root of 2 squared, that is 2. So in conclusion, found out that OF squared, that is the square of the hypotenuse, equals to 2 plus 2, that is 4. Here we took root of this equation and finally found out that OF, the length of the hypotenuse OF, is actually equals to the square root of 4, that is 2. Here OF equals to 2 units in its length. And you also know that OFE is one straight line. Here point F is the center of this circle, point E is the point of the circle itself, therefore OFE is the radius of this small circle. This is equals to the square root of 2 units in itself, according to what is given us in the question. So in total, the radius of the big circle, we define the radius of the big circle as capital R. Here point O is the center of the big circle and the quarter circle also. Point E is the point on the big circle itself, therefore OE is the radius of this circle. And we already found out that OFE is one straight line, therefore OE is one straight line, therefore OE is indeed the radius of the big circle. And we know that OFE is one straight line, therefore OFE in total will be equal to OF plus FE. Only because we know that OFE is one straight line, then we can say that the radius of this circle will be equal to OF plus FE. So the radius of the big circle capital R equals to OF, that is 2, plus FE, that is square root of 2. So in conclusion, we found out that the radius capital R of the big circle or the quarter circle equals to 2 plus square root of 2. Okay. Yeah, repeat again. Capital R equals to OF plus FE. Capital R equals to OF plus FE. OF equals to 2 and FE equals to the square root of 2. Therefore, in total, capital R equals to 2 plus square root of 2. The radius capital R of the quarter circle equals to 2 plus square root of 2 units in its length. Repeat again that our mission is to find out the area of this the shaded area, or the value of the shaded area. What is the size of this shaded area? The size of this shaded area will be equal to the area of sector AOE. This is sector AOE minus the area of the semicircle minus the area of the orange shape. Here we know that, repeat again, the shaded area, the value of the shaded area equals to the area of sector AOE minus the area of the semicircle minus the area of the orange shape, the orange small shape VHO. But first of all, how we know that this is a semicircle? We know that OFE is one straight line. If OFE is one straight line, then edge E is also, that edge E is part of OFE. Therefore, it must be also a straight line, because a part of a straight line must be also a straight line. So edge E is a straight line. If edge E is a straight line, it is a straight line that touches the circle at points edge and E. And any straight line that touches the circle at 2 points must be defined as a chord. Therefore, edge E is a chord because it touches the circle. It is a straight line that touches the circle at point edge and E. Okay, so and the straight line edge E passes through point F. That is the center of this circle, according to our definition. And you know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, edge E that passes through point F, that is the center of the circle, must be the diameter of the circle. So edge E is the diameter of the circle, and we know that any diameter of any circle bisect the circle to 2 halves. Each half is a semicircle. So this is a semicircle and this is a semicircle. Why? Because the chord edge E, that is the diameter of the circle, bisect this circle to 2 halves. Each half is the semicircle. This is a semicircle and this is also a semicircle. Therefore, we can arrive to the conclusion that this is indeed a semicircle. Therefore, the value of this shaded area will be equal to the area of sector AOE minus the area of this semicircle minus the area of the orange shape HBO. Repeat again. The value of the shaded area equals to the area of sector AOE minus the area of the semicircle minus the area of shape PHO. What is the area of a sector? We have here a circle. AOB is defined as a sector. Here we have, this is how we write down the area of sector AOB with this sign above AOB. It means the area of sector AOB. The area of sector AOB will be equal to pi r squared, that is the area of the circle, times theta over 360 degrees. Theta is the angle between the legs of this sector. The two legs are AO and OB. The two legs are also the radius of the circle, that is R. So the area of any sector equals to pi r squared, that is the area of the circle, times the angle between the legs of the sector, that is theta here, over 360 degrees. Okay? Here we can implement this formula in order to find out the area of our sector, sector AOE. AOE. So the area of sector AOE the area of this sector AOE will be equal to, here the two legs of the sector, they are equal to capital R, that is actually the radius of the big circle, that the quarter circle is part of it. Okay, so it is pi times capital R squared, because related to the big circle, it is this sector is part of the big circle, of course. Therefore, pi r squared is pi times the big radius of the big circle. Pi times capital R square times the angle between the legs of this sector, that is equals to 45 degrees over 360 degrees. Okay, again, the area of sector AOE is equals to pi times capital R squared, that is the area of the big circle, times the angle between the legs of the sector, that is 45 degrees, over 360 degrees. The legs of the sector are the two radii of the big circle, that is equal to capital R, of course. Okay. We have already found out that capital R equals to 2 plus square root of 2. If capital R equals to 2 plus square root of 2, it means that R squared will be equal to 2 plus square root of 2 square. And 45 degrees over 360 degrees, it is 1 over 8. 1 over 8. So we have to divide this expression by 8. So we have here pi, and inside the brackets we have 2 plus square root of 2 square. 2 plus square root of 2 square equals to 2 squared, that is 4, plus square root of 2 squared, that is 2, plus 2 times square root of 2 square. 2 times square root of 2 square, according to the algebraic identity, that a plus b square equals to a square plus b square plus 2 times ab, divided by 8. So we have here pi, inside the brackets we have 4 plus 2, that is 6, 2 plus 2 is 4, so in total this expression equals to 4 times square root of 2, divided by 8. Here we divided both the numerator and the denominator of this expression by 2, and in the numerator we have pi times 6, and 6 over 2 is 3, so we have pi times 3, and here we have inside the brackets 4 times root of 2, and 4 over 2 is 2, so after we divided this expression by 2, we left only with 2 times root of 2, and we have to divide the denominator 8 by 2, so 8 over 2 is 4. So in conclusion, we found out that the area of sector AOE, is equals to pi, inside the brackets we have 3, plus 2 times root of 2 over 4 square units. In the next step, we have to find out the area of the semicircle. The area of the semicircle, the area of any semicircle is the area of the circle over 2. Therefore, the area of the circle is pi r squared. If we divide the area of the circle by 2, we get the area of the semicircle. The radius of the small circle equals to square root of 2, therefore r squared is square root of 2 square. So it is pi times square root of 2 square over 2. Square root of 2 square is 2. So in total, in the numerator of this expression, we have pi times 2 divided by 2. 2 over 2 is 1, so we left only with pi. In conclusion, we found out that the area of this semicircle is equals to pi square units in its length. So now, the only thing that is left to find in order to find out the value of this shaded area is to find out the area of the orange shape, HBO. Okay, so the area of the orange shape, HBO, is equals to the area of the right and associated triangle FBO minus the area of the small sector FBH. Again, the area of the right and associated triangle FBO minus the area of this sector, the small sector FBH, will be equal to the area of the orange shape. Repeat again. The area of the orange shape BHO equals to the area of the right and associated triangle FBO minus the area of the small sector of the small circle, that is FBH. The small sector of FBH, that is part of the small circle. So the size of shape BHO is equal to the area of the right in the associated triangle, triangle BFO. The area of any triangle is the base of the triangle times the height to the base over 2. The base and the height, they are equal to each other and their lengths. The base is square root of 2 and the height is also square root of 2. Again, the base is square root of 2 times the height that is also square root of 2 over 2. Square root of 2 times square root of 2 is 2 and 2 over 2 is 1. So in conclusion, found out that the area of this isosceles and right triangle, triangle FBO, it is equal to 1 square unit in its length, and we have to subtract from the area of the isosceles and right triangle FBO the area of the small sector of the small circle FBH. The area of any sector is the area of the circle times the angle between the legs of the sector over 360 degrees. So here we focus on this small sector FBH. We know that the legs, each leg is the radii of the small circle that is r, and r equals to the square root of 2 units in its length. And the angle between the legs of this sector equals to 45 degrees. Therefore, the area of the sector FBH in total will be equal to pi r squared, that is the area of the small circle, times the angle between the legs of the sector, that is 45 degrees over 360 degrees. So pi r squared and 45 degrees over 360 degrees is 1 over 8. So we have to divide this expression by 8. So it is pi r squared over 8. R equals to square root of 2. If R equals to square root of 2, it means that R squared equals to the square root of 2 squared. So in total, the area of the orange shape FBH, or the area of BHO, of the orange shape BHO, is pi times square root of 2 square over 2. Square root of 2 square is 2. So in total this expression equals to pi times 2 over 8. Here we divided both the numerator and the denominator by 2 and found out that here 2 over 2 is 1. So here we left in the numerator only with pi, and 8 over 2 is 4. So in conclusion, found out that the area of sector, the small sector FBH, is equal to pi over 4 square units. And therefore, in total, the area of the orange shape BHO is equal to the area of the right triangle FBO, that is 1, minus the area of the small sector FBH, that is pi over 4. So in total, the area of the orange shape BHO equals to 1 minus pi over 4 square units. And the area of this shape SBE, the shaded area, equals to the area of sector HOE. And the area of sector HOE is pi times 3 plus 2 times square root of 2 over 4, minus the area of this semicircle, that is equals to pi, minus the area of this orange shape, that is equals to 1 minus pi over 4. So here we open the brackets and found out that the area of the value of the shaded area equals to pi times 3 plus 2 times square root of 2 over 4, that is the area of sector AOE, minus pi, and we open the brackets here. After we open the brackets, we have here minus 1, and minus times minus is plus. So it is plus pi over 4. And here we have minus pi plus pi over 4 is minus 3/4 pi minus 1. So in total, we found out that the value of the shaded area equals to pi times 3 plus 2 times square root of 2 over 4 minus 3/4 pi minus 1. Here we actually multiplied 1 by 4 and then we divided it by 4 in order to account factor with these two expressions. And in conclusion, found out that the value of the shaded area equals to pi. Inside the brackets we have 3 plus 2 times root of 2 minus 3 pi. And here someone said that we multiplied minus 1 by 4 and then we divided it by 4 in order to account factor with the other two expressions. So the value of the shaded area, here we open the brackets in this expression. So pi times 3 is 3 pi, and pi times 2 times root of 2 is 2 times root of 2 times pi. We have also minus 3 pi minus 4. 3 pi minus 3 pi is 0, so those two expressions will get cancelled, and we left only with 2 times root of 2 times pi minus 4 divided by 4. Here we divided both the numerator and the denominator of this expression by 2. 2 times root of 2 times pi over 2 is root of 2 times pi, and minus 4 over 2 is 2, and here we divided the denominator 4 by 2, and 4 over 2 is 2. So in conclusion, found out that the value of the shaded area equals to either square root of 2 times pi minus 2 over 2 square units in size, or in terms of numbers, the size of the value of this shaded area equals to 1.2214 square units. Okay, thank you very much.